Hello everyone, so welcome to our video lecture. So dear students, in our last video we have discussed about rearrangement in carbocations. Okay, so let us continue with the same topic. Here I am going to discuss you about ring expansion and contraction. Now let us first understand what is the meaning of ring expansion. Suppose if we say the ring strain, as we have already studied in isomerism as well about Bayer's angle strain theory. So you all know about 3-member ring, 4-member ring, 5-member ring and 6-member ring. Among these 4 type of rings, 3-member ring is having internal angle 60 degree. But as per sp3 hybridization, it should be 109 degree 28 minute. So there is a strain of approximately 50 degree. And for 3 angles if we have to count. So the strain is higher in case of 3-member and comparatively lower in 4-member, even lower in 5-member, and most stable ring is 6-membered ring. Okay, so let us understand. Suppose you are given a carbocation in which there is a 4-membered ring, then what is the possibility? If that ring can expand itself to make 5-membered ring such that the carbocation in 4-membered ring becomes and expands to 5-membered ring carbocation, then definitely it is going towards more stability. So the compound will prefer to rearrange itself in such a way that its ring expands. Okay, so let us understand using some examples. First of all, understand this case. This is 4-membered ring and in front of 4-membered ring you are having CH2 plus carbocation. Okay, so in this carbocation, if I say that there is a possibility of what? Hydride shift. You may think, as per our last lecture, it is 1 degree carbocation. If you make 1,2H minus shifting, what you will get? You will get, here you will get 3 degree carbocation. Okay, now here understand one thing. See, this carbon is sp3 here, this is sp3 having 109 degree 28 minute. No, it is not having 109 degree 28 minute. The internal angle is 90 degree. So there is a strain of approximately 20 degree strain, if I should say perfectly. Okay, now here what happens? If the carbocation due to rearrangement, this becomes sp2 carbon. For sp2 the bond angle should be 120 degree, but here it is not 120 degree, it is 90 degree. So the strain is 30 degree. Now if you compare in between these two, then due to hydride shifting, you can see the stability has even decreased. So in such cases, you cannot make hydride shifting. Okay, clear? Let me give you one more example. Here also I have made hydride shifting, 1,2H minus shift. Okay, now here you can see this is a very famous compound generally called as CPM, cyclopropyl methyl carbocation. CPM carbocation, cyclopropyl methyl means from methyl you are having from CH4 methane, CH3 and 1 valency free. If it is carbocation, so it is methyl carbocation, and in that methyl carbocation you are having cyclopropyl, so it is cyclopropyl methyl CPM carbocation. Okay, now in this cyclopropyl methyl carbocation, if you make hydride shifting here, what will happen? It will again convert from sp3 to sp2. So bond angle, internal angle is 60 degree in both cases, but here sp3 it should be 109 degree 28 minute, and for sp2 it should be 120 degree. So you can see angle strain is increasing in this hydride shift as well. Clear to you? So this is not possible again. Okay, now let me give you one more example. Now what do you think? If I make 1 2 H minus shift here, what will happen? From this shifting, this will become CH3 and this become plus charge, and this, now here in this case the ring becomes aromatic due to 2 pi electron, ring is cyclic, complete resonance in entire ring. See, it is cyclic, all atoms are planar, in ring, inside ring I am telling, okay. Cyclic, planarity, all atoms are planar, sp2 hybridized, complete resonance in entire ring, there is complete delocalization of pi electrons, 2 pi electron, so it is aromatic. So students, in this case hydride shift is possible. So I think you can understand in several cases it is not necessary that 1 degree to 3 degree rearrangement will always give you more stability. There are chances where you cannot get more stability due to ring strain. So what will happen in case of rings? Let us understand. 3-membered, 4-membered, 5-membered, 6-membered. Here I have to also discuss about a few case of 7-membered ring. Okay, so first of all you understand this is 3-membered ring. Okay, so this is 4-membered, 5-membered, 6-membered and 7-membered. Angle strain. If I have to say general case, then 3-membered ring has approximately 27 kilocalorie of per mole of angle strain. Okay, a rough figure I am telling you, approximately 27 kilocalorie per mole angle strain. Now when we say about 4-membered ring, this angle strain is decreased because the ring becomes even relatively more stable. So this is approximately 26 kilocalorie per mole. Okay, but when you come to 5-membered ring, the strain decreases to a very large extent of approximately 6.5 kilocalorie per mole. Now when you say 6-membered ring, as we all know that 6-membered ring is the most stable ring having 0 degree angle strain. So approximately, so in some cases you will find 0 kilocalorie per mole angle strain, or in some cases you may find approximately 0.4 kilocalorie per mole approx. Okay, I am giving you a rough figure only. Now when you say 7-membered ring, now what will happen? Now here comes the thought, which is more stable, 5-membered or 7-membered. So if I say the angle strain value, the 5-membered and 7-membered ring have approximately same, but in rough figure if I say, then it is having lesser angle strain, 6.3 kilocalorie per mole. Okay, angle strain. So I think you all have understood that out of 3-membered, 4-membered, 5-membered, 6-membered and 7-membered, 6-membered ring is most stable ring. So the question arises, suppose you are having 4-membered carbocation, 4-membered carbocation ring. What will be the tendency of this ring? To expand itself to make 5-membered. This 5-membered carbocation will have tendency to become 6-membered carbocation ring. Okay, this is called your ring expansion. Clear? Why it occurs? To attain stability. If the 5-membered ring becomes more stable, then definitely the process will be spontaneous and it will go fastly. Okay, Now let us take a few examples of ring expansion, how it occurs. So remember one thing, 4-membered will tend towards 5-membered, 5-membered will tend towards 6-membered, but if I say about 6 and 7-membered, so 6-membered will not go to 7-membered, but 7-membered ring has a tendency to convert itself into 6-membered ring. So this is your ring contraction. Why? Again to attain stability, okay? And this part is your ring expansion, okay? There are very few cases of ring contraction actually which are found or studied in organic chemistry. There is one more special case. See, 4-membered ring will go towards 3-membered ring. This is also a case of ring contraction, okay? So this is one case and this is one case, two cases we will be discussing, okay? Also, if you come across some example of 8-membered to 7-membered, then 6-membered, that is also possible, okay? Now understand, 4-membered to 6-member, that is possible. Stability increases. Possible. But if I say the reverse, 6-membered to 4-membered, it is not at all possible. Why? Because it will become highly unstable due to strain increment, okay? So I think this part is clear to you all. Ring expansion, first case. So dear students, understand it very carefully. If I say about JEE mains, advanced or NEET examinations, then this is one of the most favored question asked in the examination, okay? In cases of addition reactions or dehydrations, as I discussed in my last lecture, what is the application of ring expansion, ring contraction or rearrangement is in addition and elimination reactions, and in many cases in substitution reaction as well, okay? So in different types of reactions, ring expansion, rearrangement and contractions are used. So understand it very carefully. See, if you are having any 5-membered, 4-membered rings, and in front of exactly that ring, if you are having such carbocation plus charge, then what happens? This part, any side, this part has a tendency to break down such that this is your delta negative end and this becomes delta positive end. So what will happen? This delta negative end will attract towards the delta positive side, okay? And this part is break on. So what you will get? You will get see, this part I am just drawing you to let you know, dotted. This is your delta positive, delta negative, and this was your having plus charge, okay? So this is your bond breaking and this is your bond forming. Here bond forming, here bond breaking, okay? So what will happen? From this side bond is breaking, so you positive charge will come here and this negative and positive will make 6-membered ring. How? You can count here. 1, 2, 3, 4, 5, 6. So you can make 6-membered ring, okay? Now this carbon will become plus charged. Clear to you? Now sometimes what happen? Sir, which carbon went to plus charge? So I am just making a numbering. Suppose it is 1, 2, 3, 4, 5, 6, okay? So here what has been done? 1, 2, 3, 4, 5, 6. So here this is your again 1 as it is. 1 is connected with 6, 5, 4, 3, 2. You can see 1 is connected to 6, this bond, okay? So 2 and 6, the bond between 2 and 6 has been broken, 2 and 6. Clear to you? So this is a simple example of ring expansion, 5-membered to 6-membered, and hence you can say that the stability of carbocation has increased. Clear? You can check here, it is having 1 alpha H, it is having 4 alpha H, okay? Now the question arises in your mind, sir, there is one more possibility in the given question. Suppose you make 1,2 hydride shift. Okay, what will happen? This will become CH3 and this will become carbocation. Now you can count hydrogen, alpha H. 3 plus 2 plus 2, 7 alpha H. So you may have this query, sir, it is having 7 alpha hydrogen, it is having 4 alpha hydrogen. But dear students, with respect to alpha H increment, just 3 alpha hydrogen has increased. Okay, but if I say about angle strain, the angle strain here, it is having approximately 120 degree and it should be approx 110. So there is 10 degree angle strain for each carbon. Here it is 0 degree angle strain. So you can understand alpha H has increased only 3 alpha H increment, but angle strain is completely decreased. Okay, so this will not go in this pathway. This will go towards this pathway. Okay, so always remember the preference order will be ring expansion favored, then causes hydride shift, then causes methyl shift or R minus shift, then causes pH minus shift or pH group shift. Okay, clear to you? So ring expansion is favored over hydride shifting or alkyl shifting or phenyl group shifting. Clear? Okay. For this question, try yourself. Here what will happen? See, this is a carbocation. Here, don't try to break the ring when there is ring and in just front of ring means adjacent carbon outside the ring is having positive charge, then there is a possibility of ring expansion only. Okay, here you cannot make ring expansion at a time. When you are having ring and in just front of the ring, outside ring, you are having plus charge, then only ring expansion is possible. So first of all, what we need to do here is, first you can make hydride shift. Okay, now I am taking the cases together. First hydride shifting, then rearrangement, ring expansion. Plus charge will come here. See, this is having CH2. 1 H will come here, H minus, so plus charge will come here. Okay, now this ring, this will break such that this will form 5-membered ring. So what you will get? First draw 5-membered ring. Okay, now see, I am telling the exact simple path. First it will become 5-membered ring. Suppose this carbon is having one methyl. Suppose this is that methyl. So adjacent to methyl, this carbon will gain plus charge. So adjacent it will gain plus charge. Clear? Now I can show you by numbering simply. Suppose this is 1, 2, 3, 4, 5 and 6. Okay. So this is your 1, 2, 3, 4 and this carbon 5. See, from 1, 4 bond has broken and 4, 5 is connected. So 4, 5 is connected, 1, 4 is broken and now it is 6. Clear? Now again you are having one possibility of what? Now you can make again hydride shift, H minus. Okay. In this way, you got the most stable form of carbocation. Okay. Now dear students, sometimes you get this thought, sir, why don't you make one more shifting so it will become plus charge here, then you can make it 6-membered ring. Okay, you can think about it. So listen, in every step you need to get the more stable form, then only rearrangement will occur. Suppose if I make again hydride shifting H minus, what you will get? Plus charge here. In this case, ring expansion is possible, but from this to this, such rearrangement is not possible because this is more stable, having 2 plus 2 plus 2, 3, 7 alpha H, and here it is having 1 alpha H. So this is not possible. Okay. So if this step is not possible, so you cannot make it 6-membered ring. Simple. So don't confuse. Always remember the next step after rearrangement must be more stable than earlier one. Then only ring expansion or rearrangement will occur. Otherwise it will not occur. Clear? Note it down. Okay, so dear students, here I have given you two cases. In these two cases, you have to find the most stable carbocation if there is possibility of ring expansion or rearrangement or any other case. Okay, try by yourself first of all. Okay, in first case you can understand this 5-membered ring and in front of it there is one plus charge. So there is definitely a possibility of ring expansion. Do it. So you will first of all make what? This is del minus, this is del plus. So here you will get 6-membered ring. Draw it. 6-membered ring. Okay. Now in this 6-membered ring, you can understand. Now this carbon is having 2-methyl. So this carbon suppose is having 2-methyl. Then adjacent to this carbon, the next carbon from this side or this side, no issues. You can make the numbering and understand. So the next carbon will be getting plus charge. So it is plus charge. Now remember, this is not the most stable. Again there is a possibility of what? You are having methyl shift here. Why? Because adjacent to this, if this methyl shifting, yes, in ring also there is a possibility of methyl shifting, CH3 minus. Okay. 1, 2, CH3 minus shift. Now what you will get through that? Plus charge will be here. Now you can see in this carbocation you are having 3 plus 2 plus 1, 6 sulfides. So this is the most stable carbocation formed. Okay, that is the answer. Now here understand, this is one very beautiful question. In this, with respect to this 5-membered ring, see, this is del minus, this is having del plus. With respect to this 5-membered ring, you are having plus charge in front of this 5-membered ring. So there is definitely a possibility of ring expansion. So what you will do again? Just make dotted line like that. So these two will be connected. So just do what you observe. Okay. You won't be making any mistake then. 6-membered ring as it is. Now this side was as it is from this carbon 1, 2, 3, 4, 5, but it will be connected to this one. So this was as it is 1, 2, 3, 4. It was connected to this one. Now this will be connected to from this carbon 1, 2, 3, 4. If I am telling 4, okay. So this is 1, 2, 3, 4. Now this will be connected from not this one, from this one. So this will connect to this carbon. Okay. Here you can see this is 6-membered ring. This is again 6-membered ring. Clear? Now what will happen? 4. This will connect here. So this part will be getting positive charge. So this will become positively charged. If I will draw it properly, what you can see? See, these two carbon are bridging carbons. This will again get 6-membered. From downside, this is having plus charge. So this is the most stable case. Okay. So in this way also you can make ring expansion. Okay, so dear students, here I have drawn 3 cases. In these cases, find out by yourself the most stable carbocation. If there is a possibility of ring expansion, you can consider hydride shift or any group shifting. Okay, do it by yourself first. Okay. So let me see first of all, in this case, it is 6-membered ring, so most stable form only. But here is a possibility of what? From this carbocation 2 degree, you can make here hydride shifting first of all. The first case is hydride shifting. Okay. Then you will get 3 degree carbocation. So do it first of all. Okay. So this is H minus shift. 1, 2 H minus shift. Okay. Now this is having 1 plus 2 plus 2, 5 alpha H. But if it is possible to make one more H minus shift, where? Here. This is also 3 degree. So if we make again hydride shift, what will happen? You will get this carbocation. Now this is having 3 plus 3 plus 1, 7 alpha H. So you can understand this is the most stable form. Now you may come across one thought, sir, this is 6-membered and in front of ring there is a positive charge, but you cannot make it 7-membered. That will not be more stable. Okay. So 6-membered is most stable. So that is the most stable form. In this case, it is 1 degree. First hydride shift 2 degree, then again hydride shift 3 degree, and this is having benzene ring, so most stable form. So H minus shift first, what you will get? PH, CH, CH3, CH2, no, this will not be CH2, CH plus and CH3, okay? Hydride shift, this one hydrogen shifted here. Now, again, what you will make? Hydride shift. See, I have told you earlier, if there is hydride shifting possibility, then don't make. See, you are having all three cases possibility: methyl shifting, phenyl shifting, or hydride shifting. So hydride shifting is the most favored case. H minus shift, and you will get PH, C plus, CH3, then CH2, CH3. Okay, so most stable form, right? Resonance is stabilized as well as 5 alpha H. Now check this one. See, in this one you can observe in 5-membered ring there is a plus charge. So just break this part. Okay, so this will become what? 6-membered ring. So first directly make 6-membered ring. Okay. Now, if this is the ring, then del minus and del plus. So the carbon having methyl will get positive charge. So this is methyl having positive charge. So this is the only possibility. Now if you are not understanding this, let me make the numbering. Suppose it is 1, 2, 3, 4, 5, 6, and suppose this is 7. Okay. Now what you did? You did what? 1, this part is 2 as it is. What you did? You broke 2 and 6 and you just joined it with 7. So this will be your 3, 4, 5, 6, 7. So 2 and 6, you broke this from 2, 6 and you made 2, 7, then 7, 6. Okay, 2, 7, then 7, 6. Clear to you? So this was the simple case, 3 cases. I think you have understood very clearly. Okay, so dear students, in these given cases, you have to find out the order of stability of these carbocations. Okay, so let's check one by one. In this case, this carbon is having positive charge with 3 phenyl rings, benzene rings. Okay, so it will be most stable as compared to this one. It is having 2 benzene rings and H. Now check, this is having 2 benzene and H. It is having 1 benzene and 1 CH3, 3 alpha H. So this will be more stable. Why? Maximum resonance, a little lesser. Now here even lesser resonance. Now if you check this one, PH, CH, so resonance is common, but here it is having CH3, it is having 2 hydrogens, no CH3. So this is the order. Okay. Now in second case, it is having resonance. Okay. It is not having resonance, it is having 2 plus 3 plus 2, 7 alpha H. So definitely resonance is higher than hyperconjugation. Now check this one, same resonance. If I say here 5 RS, okay, in this one it is having 9 alpha H. See, it is your tertiary butyl carbocation. Tertiary means 3 degree, butyl for 4 carbon, carbocation. So it is see, I am explaining it properly because it is one exceptional case where this part becomes more stable. Tertiary butyl carbocation is relatively more stable as compared to benzyl carbocation. Why? Because in this case, it is having 9 alpha hydrogen, and this is highly stable. No ring strain, no strain is here. Why? Because if there is fourth group available, then it will be highly hindered. Okay, because this carbon can make sp3 with 109 degree, 28 meta, and these are 4 bulky groups, so it will become unstable. So suppose here it is halogen having Cl, so Cl releases, it becomes carbocation, highly stable case. Okay, so remember this is one exceptional case, this becomes more stable than this one. Clear to you? Second case, you are having this cation, suppose. Now here what you have to do, you have to make first of all what? Ring expansion. How you will do? See, this is 5-membered ring. From this part, this oxygen is having lone pair. So you may say, sir, this can make a ring expansion like this. No. Why? Because you can break this ring, you have to make breaking of carbon-carbon bond. Okay, so this is delta positive, this is delta negative. So this will join here, so it will become 6-membered ring. So you can make first of all 6-membered ring. Now understand, adjacent to oxygen will become positively charged and this bond will break. Okay, you are breaking this bond. Okay, and now this oxygen will be connected to this carbon, adjacent to this carbon is CH2, which will join here. Okay, if I make numbering, you can understand. Suppose this is 1 2 3 4 5 and 6. So what will happen? 1 2 3 4 5 and 6. Okay, so what happened actually is, you broke this side 4 and 5 and you joined with 6. So this 4 joined with 6 actually. Oxygen is connected to 5 only as it is, and you broke this 4 and 5 bond, and this is joined here like this. Clear? Now what happens? In that case, plus charge will come to this 5th carbon, this plus charge here. So it is having conjugation with this oxygen. So finally what you are getting is highly stable form of carbocation. Okay, it is having conjugation, resonance stabilized. You can say back bonding case. Okay. Okay, so students, in these two given cases, now you have to find out the most stable form of carbocation. Okay. See, in first case, you can see here, this is having 4 alpha hydrogen. You cannot make it shifting this side. But if you make hydride shifting this side, so by 1 to H minus shifting, what you will be getting? You will be getting plus charge here, which is resonance stabilized. Okay. So remember such cases, here you are having 4 alpha H, here you are having resonance stabilization with 2 alpha H. So stability has increased. So such rearrangement is possible. See, this is a case here, delta plus, delta minus. This bond is breaking. Okay, and you will join it here. There is a possibility of what? 5-membered to 6-membered ring. So first draw 6-membered ring. 6-membered ring is done. Now in this 6-membered ring, what I will do? This carbon is joined here. Okay, so this carbon is joined here, suppose. So from that, it is having plus charge. So from this carbon, this will get plus charge. From this carbon, this side, adjacent to that, this is having conjugated plus pi bond. So this is a possibility. If I'll make the numbering, see, by making numbering you will not confuse. 1 2 3 4 5 6. Okay, this is 6. Now what you did? You connected 1 with 6, 1 with 6, 5 4 3 2. Okay, so 1 2 is as it is. 2 6 is broken, 2 6 is broken. Clear to you? So 2 is having positive charge. Now it is resonance stabilized, highly stable carbocation. Okay, I think it is clear to you all. Ring contraction. Now dear students, understand, ring contraction is a very different case which is studied in organic chemistry in very few cases only. What happens? If you are having 7-membered ring, to attain stability, it becomes 6-membered. Okay. And one more case studied is 4-membered to 3-membered. And that is a special case of CPM carbocation only. Okay. You remember cyclopropyl methyl carbocation. In such case only that is possible. Okay. I am just telling you an example. Case 1, 4-membered to 3-membered ring. Cyclobutyl carbocation. Here understand, if this bond shift such that it becomes here, what will happen? First of all, join this one. See, this is del minus, del plus. Okay, Now by making 3-membered ring, what you did? This part is broken, minus plus, it is joined. So this part is broken, so it is having, this part is having your CH2 part, CH2 plus. Now if I make it properly, it is like this, CH2 plus. Okay. Now why it is becoming more stable? You may have this question in your mind. It is sp2, it should be 120, here internal is 90, so it is having angle strain of 30 degree. Here what happens? 60 degree. In 3-membered ring, angle strain is increased. But one more thing happens. This structure of 3-membered ring, cyclopropyl methyl carbocation, have a tendency that it bends such that this bends towards this side, such that these bonded electrons have a tendency to donate its electron pair to this side, which is generally called as dancing resonance. Okay. And in that way, this cyclopropyl methyl carbocation becomes highly stable. So this ring is highly stable. Okay. So there is a tendency of 4-membered ring to convert into 3-membered ring. So this is called as ring contraction. Okay. You can note this case. Case 2. Now students, understand this case. Here you are having 7-membered ring. Okay. Suppose if I say 1, 2, 3, 4, 5, 6, 7. See, in 4 to 3, I told you about extraordinary stability of CPM carbocation. How dancing resonance and all such cases. Okay. So that is stable. In 7-membered ring also it has been observed. How? Suppose if this bond number 2, 3 is broken such that it is delta positive, it is delta negative, and this part combines with carbon 1, what will happen? You will make 6-membered ring first of all. So what you did? You joined 1 with 3, okay, 4, 5, 6, 7. Now from carbon number 1, this is outside. How? You broke this bond, okay, such that it is 2, it is 3, it is having delta negative part. So this carbon is having CH2 plus, this one is having CH2 plus. Okay, clear to you? So from ring contraction you made this carbocation. Clear to you? Plus charge comes here, right? Now what you can do, here there is a possibility of hydride shifting. So what you will make? You will make 3 degree highly stable carbocation. So this is a case of ring contraction followed by rearrangement, hydride shifting. So ring rearrangement, then hydride shifting, again rearrangement to make the most stable form of carbocation for this case. Okay. See, dear students, here I am using one special case of 7-membered ring contraction. Okay, in this question, what happens? See here, this is having positive charge, this is having this bond. So again, see, 1, 2, 3, 4, 5, 6, 7. Okay, so what we have to do again, ring contraction means 1,6 combination. So this will break such that it is del minus, it is del plus. So you just join it here. So what you will get? First of all, make 6-membered ring. Okay. Now you joined 1, 2, 3, 4, 5, 6. So 6 is joined it 1. 1 is having 1 methyl as it is. Now this carbon is having methyl. Again, this is joined with this group, this carbon, which is having 2 methyl, and plus charge will come here. So this is the most stable form possible for this case. Okay. Now I am taking one more case of rearrangement. Suppose you have this ring with plus charge here. Okay, now you understand what will happen in this case. See, it is having again 1, 2, 3, 4, right? If you make from this side 1, 2, 3, 4, that is okay, no problem. So again, what I will do is, I have two possibilities. Either I can break this side bond or this side bond. Okay, so if I break this bond such that delta positive comes here, because this will form more stable carbocation, so this will be broken such that join 1 with 3. So first make 3-membered ring, 2 and 3. Okay, now from 2 position you are having 1 methyl. Okay, now from 3 position it is already broken. So from 1 position what you have? You have 1 carbon. You have 1 carbon which is having 2 methyl and having plus charge. Now you can see simply this is again one of the stable form. It is CPM style. Okay, cyclopropyl methyl carbocation, and it is having this side and this side 2 methyls, so even higher stable case. Okay, so in this way, dear students, you can study about ring contraction, all the cases. Okay, so dear students, in this case you have to make rearrangement and form its most stable carbocation. Now understand, in such cases what happens? First of all, you are having here resonance, so make it RS, double bond will come here, it will come here, and you will get here plus charge. Now here, now you can say this is 5-membered, and in front of 5-membered you are having plus charge, so you will be having ring expansion. This bond will break, you will get plus charge here. This is delta minus, this will be joining here. So what you will get? This 6-membered ring, this 6-membered ring, this will be bridged. Okay, so I am drawing here this part as it is. Okay, as it was. Now from here, this side what happened? This bond break, this part. See, suppose if I say this is 1, 2, 3, 4, 5, so what will happen? This is 1 as it is. Okay, 2, 3, 4, 5, and this 5 will join with this part, so it will join with this part as it is. Now this will become positively charged. This is having pi bond, this is having pi bond. Okay, now in this way, this is the most stable form. It will be having resonance, so plus single double type conjugation. So this is the most stable form possible for this. So in this way you made this 6-membered and 5-membered finally into 2 6-membered rings, and bridgehead is having positive charge. Now you may come across Brett's rule, bridgehead portion cannot be plus charge. So here bridgehead portion can be plus charged. Why? Because if the ring is less than 8-membered or 8-membered, then it is not possible to have plus charge at bridgehead. But if it is higher than 8-membered, then it is possible to have plus charge on bridgehead portion. Remember this rule. Why? Because if it is having plus charge, then it must satisfy the planarity rule. If it is plus charge means sp2 trigonal planar. So here there is no issue of planarity. One is this side, another this side, another this side. So it is not possible here. You are having 6 plus 4, 10-membered ring. Okay, clear? So dear students, here we studied in detail about ring expansion and ring contraction. Okay, so we'll continue in our next lecture.